Okay, so we're doing the comparing estimators exercise. This is part of week 5, biased estimators, variance and least squares. So if you open the REPL to that exercise, you get these two functions that you're meant to complete. And this is the code that it imports the data from this DAT file, and the code that actually plots the result of the functions you write. So the point of this exercise is to compare using the block averaging technique. So if you're doing this exercise, you are assumed to have completed this one, calculating block averages, in which you use block averaging to essentially just like if you have a set of data, you divide it into n blocks, and then you get the average for each of those n blocks. And then you divide it over the size of that block. So you're meant to use that technique in this exercise. So what we need to do is use that technique to calculate 10 estimates for V and 10 estimates for V prime, where V is the result of this expression here, where R sub I is the ith element in the list of radiuses we have, which is in bubbles here, bubbles.dat. This is a list of radii. And similarly, V prime is the result of V is 1 over n times the sum over n of all the radii cubed multiplied by 4 over 3 by pi. But V prime, instead of it takes the constant out, and then instead of summing the cube of the radii, it cubes the sum of the radii. So it gives us a different estimate for the average of volumes for these bubbles. So these are this is just the formula for the volume of a sphere, and the radii here are the volumes of different bubbles. Okay, so it says here that the first of these functions, average volumes, should return a numpy array with n blocks elements. The 0th should contain an estimate for V that is computed from the first len data n blocks data points of the data. So what that means is that we need to return a numpy array, which is this averages numpy array here, and because and it contains n blocks elements, because that's the way we set it up here using np.zeros. And what we need to do is populate this averages list with estimates for V that are computed from these bubble radii. Okay, so now we do for I in range n blocks, because we want to populate a numpy array that is n blocks long. And then we use the block averaging technique, which you can go back to the code that you've written and use this. You can define a B size or a block size using this expression here, and then you can use that block size to populate your averages list. Okay, and that's the expression we use here. So this expression says that the ith element in the averages list is the sum of the previous the previous. No, it's the sum of the data from the sum of the data from our current index all the way to the next index. But instead of being just that distance alone, it's that distance multiplied by the block size. So it's actually the sum of all the data that is in that one block. And then we divide that sum over the block size to get the average for that block. And so once we've done that, with this expression, we just have the sum of the actual data points themselves, not without any operations done to them. But that's not what we want. We want to change this expression here to fit this equation here. So since we're doing average volumes, so we're doing the volumes for this expression here. What we're going to do is that for each I, for each data square brackets I, which is the ith element in the data set, which in this case each of those is a radius. So what we're going to want to do to that radius is you want to first cube it to reach this r sub I cubed expression, and then once we've cubed it, we multiply it by 4/3, and then multiply it again by pi, when we write pi as np dot pi. Okay, so now using this expression here, what we've done is that we've reached an expression that is equivalent to this one here. Okay. And then from there we return averages. Because we're done populating the averages list, now we just want to return it. Okay, and we're going to do a similar thing for the other estimate for the average of this data set. We're going to define a block size, and we're going to iterate over we're going to iterate over for I in range n blocks, and then for each element in the averages list, which is as it stands now is an empty numpy array, we're going to populate that NP array with the following elements. So each element needs to conform to this expression here. So we've transformed this expression to fit this equation. Now we need to do a similar thing for this one, but we need to match it to the second equation. Okay. So with this one, we would need to the only thing that needs to be included inside the cube, so to speak, the cube bracket here, is 1/n and the sum of the random variables just as they are. So what we're going to do is we're going to take the sum of those random variables, which is this expression all the way up to here, without the root, so just this expression here. That's this sigma right there. Okay, and then once we've done that, we want to divide that whole expression by b size. Okay, so take this one out because we are rearranging. And then once we've done that, we want to keep the whole thing. So now this expression here is equivalent to the expression in the bracket, including the cube power here. Okay, so that's sigma r sub I over n to the power of 3. And once we've done that, we want to multiply by these constants here. And that's just multiplying by 4 over 3 and then multiplying by pi. Okay, we should take care that there's actually a syntax error in the preloaded code itself, so don't worry about that. It's just that in the preloaded code this doesn't have the second quotation mark, so just add that in and it should work. And so once you run your code, you should end up with a graph, and this is the graph. And the graph shows the various estimates of v and v prime that you have obtained in your experiment. The estimates of v are shown in blue, while the estimates of v prime are shown in red. So, as you can see here, these are from v prime, which is the expression we obtained with this equation. This is the estimate that we obtained when we used this expression, and then the blue points are of the distribution that we obtained when we used this expression for the average. So if you run your test sheet, see if the criteria is met, and it is. Hit submit, run the tests one final time, and the checkouts. So the point of this exercise is just to apply the block averaging technique that you've learned in the other exercise here. And what it wants to illustrate is the ability to include expressions as complex as these, and use that in conjunction with your block averaging technique in order to get more precise estimates, or just different estimates for when you want to have more than one value for your estimate to compare, and see which of them fit your model more suitably. So that was comparing estimators using block averaging techniques.